Alright, silly people, here's the situation. We're literally just finding the equation of motion from this Lagrangian here, um, figuring out what physical system it is, uh, finding the Hamiltonian, um, discussing the Hamiltonian, and seeing what happens when we apply initial conditions to the problem. So, equations of motion are found as normal using the Euler-Lagrange equation, which I'll just write out here. The time derivative of the partial derivative of the Lagrangian with respect to generalized velocities minus the partial derivative of the Lagrangian with respect to generalized coordinates is equal to 0. It's a one-dimensional problem, so all we have to do is x and x dot here. So let's just do these partial derivatives. Del L del x dot is just mx dot times e to the gamma t. The time derivative of that is going to have two terms. One with the second time derivative of x, and then one with the time derivative of the exponential term. Yeah. And then let's do the partial with respect to just x. It's going to be minus m omega squared x not over 2. Just minus m omega squared x e to the gamma t. Cool, so we have all our partial derivatives. We can just plug that into the Euler-Lagrange equation. All of them have a factor of e to the gamma t and a factor of m. And I don't want to jump the gun. Oh, I missed a term there, actually. I don't want to jump the gun, but all of those m's and exponential terms are going to get canceled out because it's equal to 0. You can just get rid of those guys. So we have x2 dots plus gamma x dot equal or plus omega squared x is equal to 0. If you can't tell by now, maybe writing it like x dot on one side and everything else together, maybe now you can tell that this is just a damped harmonic oscillator. Cool. Damped harmonic oscillator. Now we need to construct the Hamiltonian first by finding the canonical momentum, which we already kind of did. The canonical momentum is the same as the partial derivative of the Lagrangian with respect to x dot, which we found was that term up there, mx dot times e to the gamma t. And the Hamiltonian can be constructed if you take that canonical momentum, multiply it by x dot, and subtract the Lagrangian in terms of x and the momentum. We don't want any x dot terms. To turn the Lagrangian in our current form into a form which involves momentum, we can use this canonical momentum that we just found to solve for x dot, which is going to be p divided by m times e to the minus gamma t. Yeah, and so when we plug that into our Lagrangian, which, I have it up there, Lagrangian, we just have m over 2 times on the inside p squared over m squared e to the minus 2 gamma t minus omega squared x squared e to the gamma t. I'm going to distribute this thing, expanded I mean, just so it looks cleaner. It'll be p squared over 2m e to the minus gamma t minus m omega squared x squared over 2 e to the plus gamma t. We have a minus exponential term and a plus exponential term, which is weird, but let's keep going. Now we have everything that we need to do the Hamiltonian, which is going to be p squared over m e to the minus gamma t minus the Lagrangian, so minus p squared over 2m e to the minus gamma t plus m omega squared x squared over 2 e to the gamma t. We'll just distribute or collect those like terms until we have something that looks very much like the typical harmonic oscillator Hamiltonian, with which I am far too familiar, but just with some exponential terms, which is really weird. And so, is it a constant of motion? No, because the time derivative of it is not 0. Check it. If we just take the total time derivative of this whole thing, assuming momentum is kept constant, then we'll have a minus gamma e to the gamma minus gamma t there, and then a m omega squared x squared gamma over 2 e to the gamma t. That's not 0, so it's not a constant of motion. That's not too weird. But the last part of this question is, what if initially x is 0, t is 0, and x dot is 0? What happens when t approaches large values? It's 0. X will tend towards 0. You can justify that by just looking at the equation of motion that we solved for earlier, this guy, right here. If you just set x equal to 0 and x dot equal to 0, then you'll just have x 2 dots equal to 0. So you don't have any acceleration, initial velocity, or position, so you're just staying still. Also, if you want to rectify that with like real life, you'll just have a spring that is staying still. That's the motion of this object. All right.